So derive expressions for shear and moment and draw the shear force and bending moment diagrams for the beam shown below. Neglect the weight of the beam. Please help me promote my channel by sharing my lecture videos and sample video problems to your friends and to your friends' friends. That's the only way you can help me and to keep me energized and create more lecture and sample video problems. So here we go. For the reactions, it is half of the total load. So call that AY, AX is 0, but not important. R sub C, AY equals R sub C equals 1/2 of 4 times 80. So 1/2 of 4 times 80. So 80 kilonewtons as shown. So let's have that first section, and this is X. Let's call this WAB. This is the positive shear, and positive moment is counterclockwise as shown. And let's call that WAB. So WAB as to X equals 80 as to 2. Therefore, W sub AB is 40X. So remember, the shortcut to shear equation is upward minus downward. So shear AB equals upward AY 80 minus the area of this line load diagram 1/2 of X times WAB. So shear AB is 80 minus 1/2 of X times WAB, which is 40X. Simplifying, shear AB is 80 minus 20X squared. So that's the shear equation for segment AB. For moment, it is clockwise minus counterclockwise. So moment AB is AY 80 times X minus the moment of this line load diagram, which is 1/2 of X times 40X times moment arm X over 3. So moment AB is 80 times X minus 1/2 of X times 40X times X over 3, or the moment arm or distance of the centroid from this section here. Simplifying, moment AB is 80X minus 20X cubed over 3. So that's it. Then for the second section, so let's remove those. So there are two parts, remember, and the left portion is complicated, so we consider the right portion. The positive shear this time is upward, and the positive moment is clockwise. Then if that is X, then this is 4 minus X. And the intensity of the loading, let's call that WBC. So by similar triangles, WBC as to 4 minus X equals 80 as to 2. So WBC is 40 times quantity 4 minus X. So therefore, for the right portion, it is the opposite of the left portion. So shear BC is downward minus upward force. So downward is 1/2 of 4 minus X times WBC, which is 40 times 4 minus X. Then minus upward, which is R sub C, which is 80. So shear BC is 1/2 of 4 minus X times WBC, which is 40 times 4 minus X. So shear BC is then minus R sub C, which is 80. Simplifying, shear BC is 20 times 4 minus X squared minus 80. Then for moment BC, it is counterclockwise moment minus clockwise moment. That's the shortcut. So moment BC is 80 times quantity 4 minus X, then minus 1/2 of 4 minus X times 20 times, let's just copy this. This is the force, then the moment arm is, this is the force 20 times 4 minus x equivalent to this area of triangle here. Then we just put the moment arm, which is 1/3 of 4 minus x, 4 minus x over 3. Simplifying, moment BC is 80 times 4 minus x minus 20 over 3 times 4 minus x quantity cube. So we have completed the shear and moment equations for the two segments. We are now ready to sketch the shear force diagram and the bending moment diagram. So for the shear force diagram, shear in portion AB, which is defined from 0 to 2. So we set x is 0, so 80 minus 20 times 0 square is 80. It begins with 80. That's 80. Then when x is 2, 80 minus 20 times 2 square is 0. So it is 0 here. By the way, the other way of defining the curvature of the curve, because this is second degree curve, is to put the initial slope. Later, the intensity of the load is the slope of the tangent to the shear diagram. So this is an additional technique. So because the load here, intensity of the load here is 0, so it's 0. The intensity of the load here is negative 80, and negative 80 slope is up to the left like that. Then remember, this is 0 when x is 2. When x is 2, that's 0. So the problem is how to connect these 2 points with a curve. So you may also define the slope. So 0 here, horizontal, then negative 80 up to the left. That's like, so you'll have an idea that a curve is drawn by making it tangent to these two slopes. So it should be concave downward. The other idea, which I mentioned in the preceding examples, is to evaluate the second derivative of the curve. So first derivative, VAB prime is negative 40x. The second derivative is negative 40. So the concavity therefore is downward. That's why we should connect these 2 points with concave downward curve as shown. So there are two techniques based on the slope. For shear, it is defined as the intensity of the load, and based on the second derivative, which is the concavity. So it is negative 40, so it is concave downward. Then for the portion BC, when x is defined from 2 to 4, when x is 2, 20 times 4 minus 2, so 20 times 2 square, 80, minus 80, so it is just the continuation. It begins with 0 here. This is 0 when x is 2. Then when x is 4, this is 0, so negative 80. Put that negative 80. So how do we connect these 2 points? So first, based on slope, this is the same slope, negative 80. Here, because the intensity of the load is 0, so it is horizontal. So we are given the idea that to connect these 2 points with a smooth curve, it should be concave up, like that. And to prove, although not shown here, you differentiate shear BC twice. So I'll just dictate 20 times 2, so 40 of 4 minus x times negative 1. So the first derivative is negative 40 times 4 minus x. Therefore, the second derivative is negative 40 times negative 1. So it is positive 40. And positive 40 is concave up. So that's why we have a concave up curve as shown. So this is the shear force diagram. Then for the bending moment diagram, MABs, first set x is 0, 0 to 2. It is defined from 0 to 2, so it is 0. By the way, this is a second degree curve, so it begins with 0. Then when x is 2, 80 times 2 minus 20 times 2 cube over 3, use your calculator there. It is equal to 320 over 3. So the shear at when x is 2 at B is 0. So since the slope of the bending moment curve is the ordinate of the shear curve above, just like the slope of the shear force diagram is the intensity of the load or ordinate of the loading above, the slope of the bending moment curve is the ordinate of the shear force diagram or shear. It is shear. So first, based on slope, we have positive 80, so up to the right like that. And because this is 0, the slope is horizontal, the tangent is horizontal. So take note that at 0 shear, moment is positive. Take note, at 0 shear, moment is positive. So that's why the maximum moment is 320 over 3. Then you are given the idea how to connect these two tangents smoothly with a curve. So just make it tangent to the smooth curve. So it should be concave downward as shown. But based on concavity, if we evaluate MAB prime, it is 80 minus 20x squared. So the second derivative of moment AB is negative 40x. Since AB is defined from 0 to 2, so we assign x is 1, intermediate point. So negative 40 times 1 is negative 40. So that's why it is concave downward as check using the tangents. So like that. So concave downward because this is negative 40 times 1. So negative 40. For portion BC, when x is 2, 80 times 4 minus 2 is 160 minus 20 over 3 times 4 minus 2 cube, it will still give us 320 over 3. So it is continuous. It begins with here when x is 2. Then when x is 4, obviously this is 0 and that is also 0. So it's 0 here. Since the slope of the tangent when x is 4 at C is negative 80, so it's sloping up to the left based on slope. So again, you'll now have an idea how to connect these two tangents with a smooth curve. So it should be concave downward. But based on the concavity, we differentiate moment BC twice. So this is negative 80, then plus 20, 4 minus x squared. The second derivative is negative 80. Oh, sorry, 0. This is now 0. This was positive 24 minus x squared. So this time it is negative 40, 4 minus x. Then when x is 3, negative 40 times quantity 4 minus 3 is negative 40. So it is concave downward. So M prime BC is negative 80 plus 20 times 4 minus x squared. It's positive because it is supposedly negative 20 over 3 times 3 times 4 minus x squared times negative 1, derivative of 4 minus x, so positive 20, 4 minus x squared. The second derivative is negative 40 times 4 minus x. That's why when x is 3 between B and C, this gives us negative 40, so it is concave downward as shown. So that's it for this problem. Then for the next problem, derive expressions for shear and moment and draw shear force and bending moment diagrams for the beam shown below. Neglect the weight of the beam. So here we go. First, let's compute for the reactions. Call that AY, and R sub C, AX is 0, of course. So summation moment about C0 or moment C0, so we have AY times 7.2 plus 4 times 3.6 or minus 0.9 kilonewton per meter. Let's make it consistent. Times 10.8, the total length of the uniform load. Then supposedly the distance of the centroid from the right is 5.4. 5.4 minus 3.6 is 1.8. That's why the moment arm is 1.8. The centroid is here. 5.4 from D, but 1.8 from C, where 1.8 is 5.4 minus 3.6. Then minus 8.1 times 4.8, then plus 4 times 3.6. So solving for AY is equal to 5.83 kilonewtons. Then summation moment about A is 0. So let's put 5.83 kilonewtons. R sub C times 7.2 minus zero point 0.9 times 10.8 times 5.4. So 5.4 this time. Minus 8.1 times 2.4. Then minus 4 times 10.8. Solving for R sub C is 15.99 kilonewton. So you check 5.83 plus 15.89 minus zero point 0.9 times 10.8 minus 8.1 minus 4. It should give us 0. So let's define section AB here. Distance X, then we have shear AB downward, moment AB counterclockwise. So for the shortcut, shear in AB is upward minus downward force. So it is shear AB is 5.83 minus 0.9 times X. 0.9 kilonewton per meter times X, the area. Then for moment AB, it is clockwise moment minus counterclockwise moment. So 5.83 times X minus 0.9 times X over 2. So it is 5.83 X minus 0.45 X squared. So again, 5.83 times X minus 0.9 times X, that's the force, moment arm X over 2. So 0.9 divided by 2 is 0.45 X squared. So minus 0.45 X squared. Then let's proceed to section BC. There are 3 segments of this beam here. So remember the shortcut, previous plus minus the new shear or new moment. So shear BC positive, counterclockwise for moment BC. So shear BC is equal to previous 5.83 minus 0.9x, then minus 8.1 downward. This is the new force. So minus 8.1, simplifying. 5.83 minus 8.1 is, so shear BC is negative 2.27 minus 0.9 of x. So this is a line with negative slope, sloping downward. Another line with negative slope, first degree. This is second degree. So moment BC, on the other hand, is previous. We copy 5.83x minus 0.45x squared. Then we subtract, because this is counterclockwise. The moment of 8.1 is 8.1, and this moment arm here is x minus 2.4. So moment BC is 5.83 minus 0.45 x squared minus 8.1 times quantity x minus 2.4. Then combining 5.83 minus 8.1 x is negative 2.27 x minus 0.45 x squared, then negative 8.1 times negative 2.4 is 19.44. So that's the moment equation for BC. For CD, it will be not convenient compared to CD if we consider the right part. So let's consider the right part. So call that distance x. Therefore, this distance is 10.8 minus x. And let's consider the right portion. So this time the positive shear is upward and the positive moment is clockwise. So remember, if we consider the right section. So just concentrate here. The shortcut to shear CD, it's no longer upward minus downward, but rather downward minus upward. So these forces are downward, the load and these 4 kilonewtons. So shear CD is equal to 0.9. Downward is positive. Downward minus upward. So 0.9 times 10.8 minus x. Then another downward force plus 4. Simplifying, shear CD is equal to 13.72 minus 0.9x. While for moment CD, the shortcut is counterclockwise moment positive minus clockwise moment. So all are clockwise, so they are both negative. So MCD is negative 0.9 times 10.8 minus x times 10.8 minus x over 2, the moment arm, and minus 4 times quantity 10.8 minus x. Simplifying, MCD is 0.45 times quantity 10.8 minus x squared minus 4 times quantity 10.8 minus x. You may simplify that further or you may just leave that the way. There's no problem. As long as we plot the shear force and bending moment diagrams correctly. So we are now ready to sketch the shear force and the bending moment diagram. The shear force is in kilonewton and the bending moment diagram, the value is kilonewton meter, the ordinates. So for shear AB, set x 0, it is defined from 0 to 2.4. So 5.83 as shown. Then when x is 2.4, 5.83 minus 0.9 times 2.4, it is 3.67. Since this is just a straight line, so no problem, you just connect them with a straight line as shown. So there's no need to apply that technique because that's just a straight line. Then for shear BC, when x is 2.4, it should start at B, which is 2.4. Negative 2.27 minus 0.9 of 2.4 is negative 4.43. Then when x is at C 7.2, negative 2.27 minus 0.9 of 7.2 is negative 8.75. Since this is a straight line, first degree curve, so you just connect them with a straight line as shown in the figure. Then for CD, when x is at C 7.2, 13.72 minus 0.9 of 7.2. So it should be equal to 7.24 positive as shown. Then when x is 10.8, 13.72 minus 0.9 of 10.8, the value is positive 4 as shown. So since this is a straight line again, you just connect these two with a straight line as shown in the figure. Then it should end up at 0 because of 4, minus 4. If you proceed to just to the right of D, then it should be subtracted by 4 to make it close. So that's the shear force diagram in kilonewtons. Then for the moment curve, this is second degree. When x is 0, so this is 0, it should begin at 0. Shown. When x is 2.4, 5.83 times 2.4 minus 0.45 of 2.4 square, The value is equal to 11.4. Now, how do we connect these two with a curve, a smooth curve? So based on slope, 5.83 slope to 3.67, so it is inclined up to the right. This is also positive but lesser slope, so it is inclined up to the right but almost flat like that. And to give you the idea how to connect these 2 points with a smooth curve, it is concave downward, supposedly as shown. But based on the second derivative or concavity, MAB prime is 5.83 minus 0.9x. Then second derivative M double prime AB is negative 0.9. So it means it is concave downward as shown in the figure. That's it. Then for portion BC, substitute x is 2.4, negative 2.27 times 2.4 minus 0.45 of 2.4 square plus 19.44, it will give us the same 11.4. Then when x is 7.2 at C, negative 2.27 times 7.2 minus 0.45 times 7.2 square plus 19.44, it will give us negative 20.232. So based on slope, the slope initial is negative 4.43, so that's a negative slope approximately. Then negative 8.75 here. So it's also sloping up to the left or down to the right like that, but steeper negative slope. So to give you the idea how to connect this with a smooth curve, it should be like that, concave downward. And the other proof is you evaluate second derivative of MBC. The first derivative is negative 2.27 minus 0.9 of x. So the second derivative is negative 0.9. So it is still concave downward as shown in the figure. And finally, for portion CD, substitute at C 7.2, then you can have the same value of negative 20.232 here. Then when x is 10.8, of course, these two terms will be 0. So it ends up with 0. The initial slope is positive 7.24. The final slope is positive 4, but almost sloping like that, lesser slope. So to connect them with a smooth curve, it is concave downward again, like that. But based on the second derivative, the first derivative is positive 0.9 of 10.8 minus x, then plus 4. The second derivative would be negative 0.9. So it is still negative 0.9. So MCD prime is 0.9 of 10.8 minus x plus 4. You should know how to differentiate, or else you haven't yet finished calculus. If that's the case, if you do not know how to differentiate that function. The second derivative is negative 0.9. So it should not be a question here. How do I get this? How I got this value? So negative 0.9, so concave down as shown. So that's it. And this is the bending moment diagram. For the elastic curve, we have a portion here which is positive, then negative. This is the point of inflection where concavity changes from concave up in this part to concave down in this part. So positive moment means concave up, curvature is concave up, and for negative moment, concave down. And it should pass through the elastic curve should pass through the support, because the supports in this case do not settle. So in this portion, concave up, then concave down on that portion as shown in the figure. So that's the approximate elastic curve. And this is the point of inflection, zero moment, the point where concavity changes direction from concave up to concave down. So that's it for this problem.